All right. Example 15.5. And by the way, thank you for responding to that survey so well. Quite a few of you have responded, and I really appreciate that. Okay, so we're going to carry on with conservation of momentum. Okay, so we've got two bumper cars, A and B, right? They're heading towards each other. They're going to collide. They do collide. Okay, we have A going at 3 meters per second that way. Remember, momentum. It's a vector equation, so you need to consider the directions. And B, they both have a mass of 150 kilograms, and B is going left at 2 meters per second. Okay, the question is, if no energy is lost, that's quite an important statement. If no energy is lost during the collision, determine their velocities after collision. Okay, so we've got mass of each, and we've got their initial velocities, and no energy is lost. Okay, so why is this a conservation of momentum problem? Why? Because if we consider both particles inside our system, and when they collide, they have equal and opposite impulses, and these equal and opposite impulses are internal and they cancel out, so we have conservation of momentum. Okay, so we've got the momentum of bumper car A plus the momentum of B initially is equal to the sum of the momenta at state 2. Okay, nothing new here. Remember, we do not have any impulses, so that's 0. Okay, so we have mass times velocity of A at state 1. We have mass times velocity. Look at the minus there. There's a plus 3 because it's going in that direction, and we have a minus 2 because it's going in that, car B is going in that direction. Okay, is equal to mass times velocity of A at state 2 plus the mass of B times velocity of B at state 2. And if you solve for this, you'll see that we have one equation with two unknowns. We don't know what is the velocity of both of the cars, the velocities of both cars at state 2. Okay, now this is where this statement comes in handy to solve this problem. If no energy is lost. Okay, so what do we mean by that? Remember, if you have a ball, you drop the ball, it hits the floor, then in real life it'll come up to somewhere below where you dropped it from, right? And that is because energy is lost. We lose energy to internal energy, sound, things like that. Okay. However, here we approximate. We're assuming. Okay, we make an assumption that during that collision, no energy is lost. What does this mean? This means that in this kind of application, the ball goes back to where it came from, the same height. Okay, no energy is lost. So if no energy is lost, we can use the conservation of energy. Okay, principle of the conservation of energy. And remember, when we're talking about the conservation of energy, we're looking at the kinetic energy plus potential energy. Remember that this potential energy included the potential energy due to gravity, due to gravity and due to spring forces. So kinetic energy of the particle at state 1 plus the potential energy of the particle at state 2 is equal to that on the right. Okay, so our energy, total energy at state 1 is the same as the total energy at state 2. Now, let's look. In terms of potential energies, right, there's no spring forces, and we're not looking at gravity. So the total potential energy at state 1 is 0, total potential energy at state 2 is 0. So all we're doing is we're looking at the kinetic energies in this equation. So half mva squared plus half mvb squared at state 1 is equal to half mva squared plus half mvb squared at state 2. Okay? So the sum of the kinetic energies at state 1 is equal to the sum of the kinetic energies at state 2. Okay? So the point is that you can't solve this because you've got two unknowns. So we need another equation, and because no energy is lost, we can use conservation of energy, and we apply it, and we get these lovely things. Okay? Okay, so we've got this equation, and we've got this equation. VA2, VB2, VA2, VB2. Alright? Substituting equation 1 into 2, we get this. Okay, and because it's a quadratic, we're going to get two roots. Remember a root? What is a root? It's just simply where the curve cuts the x-axis. Okay? So, yeah, it's where the curve cuts the x-axis. So that's what we're trying to find. And we find two roots, plus 3 and minus 2, all right, for VB. And already we know that VB at 1 was 2. So VB1 was minus 2 meters per second. So that's the one root. So we know that this plus 3 must be the speed with which V rebounds, goes at 3 meters per second. Okay? Now what about A? Well, if we've got VB2, which is 3, we plug the 3 in there, and we get VA2 is minus 2 meters per second. Okay? So VA2 is minus 2. Now, you can check your answer, guys. If you had, I mean, obviously, if you choose that direction as positive, then of course this 2 is minus 2, that 3 is plus 3, because this is going in the positive direction, that's going in the negative direction. Say now you went and calculated, say a minus 3 here, a minus 3 for VB2. Then of course you know that that's wrong, because it can't keep going in that direction in this specific case. So just check your answer, use your intuition, use your logic, that this must be positive before collision and must be negative after collision. This must be negative before collision and positive after collision. Okay? So we've learned how to combine conservation of momentum and conservation of energy. See you in the next one.